This is part 3 of a 4-part webinar series looking at some of the features and functionality of Mode Frontier. If you weren't aware, we've already done a webinar on sensitivity, a webinar on response surfaces, and now today we're looking at some data mining, trying to really understand the data that we have either in design optimization or process optimization, and we're going to look at some of those features. So what I'd like to take you through today is just a very brief overview of Mode Frontier. Each time we've done these webinars, just like to give you a little bit of a flavour or background to Mode Frontier, and then this time we're going to go straight into looking at a demonstration of some of the features, and then at the end there's an opportunity for some questions and answers and any comments. Now, just to be aware at this moment, if you're online, please don't be afraid. Often that's the scary opportunity to ask any questions, but don't fear if you don't ask any questions there. Please do get in contact with your local representative and you can ask questions directly to them. So the whole purpose of this is really not to be a training or a technical insight, but more of just being aware of some of the features and some of the things you can do with Mode Frontier, either in the future or currently with your license at the moment that you have. So there are some problems that we have every day. Engineering, typically we're operating with some data somewhere, either that's experimental data or it's virtual data. There is quite a bit of complexity when looking at that kind of data. Maybe there is noise in that data, maybe there is some inaccuracies. We want to pull data from Excel spreadsheets or databases or text files, or actually from a live process. So managing that data can be quite difficult, let alone understanding it. Another difficulty with our engineering is that sometimes our data quality is poor. We can obtain a lot of data, but are we obtaining data that can be understandable? Also, do we have the tools to be able to understand the relationships within those data sets? What happens if there's many different interactions and relationships going on between particular parameters or variables? Is the quality good enough to be able to do that kind of assessment? Also, in terms of our data usage, we can often be really limited in the knowledge that we can extract. So often we're looking at data to then go on to do some subsequent analysis, and we can be severely limited in that regard as well. So these are some of the issues that we have with our engineering data at the moment. Here's just a nice quote from John Naisbitt. We are drowning in information but starved for knowledge, and there's a nice little image that describes that problem. Sometimes we're generating a lot of data as engineers, which seems very slick and very good thing to do, but are we actually using even 1% of that information that we've extracted? Can we join the dots to provide genuine knowledge that is actually going to affect our design? So what about the definition of data mining itself? It is simply the computational process of discovering patterns in large data sets. Discovering patterns in large data sets. So that's pretty much what we're going to be doing today, just assessing in some standard data from an Excel spreadsheet, and trying to understand something about the relationships of that data. And the goal is really to extract the information and then to transform it into an understandable structure for further use. So this is really a stepping stone to something much greater than trying to achieve. Maybe that's some kind of optimization or improvement in our design. So the solution that we're going to be looking at is obviously Mode Frontier, all wrapped around this idea of data mining. We need to be able to, first of all, input that data into to Mode Frontier, we need to be able to do some pre-processing, maybe set up some inputs, some outputs, give it some logic, some constraints, some objectives, that kind of thing. We then need to be able to analyze that data, use some charts, that kind of thing, and then in the end make some assumptions, make some tests, and actually validate that some of our hypotheses are true, and we can do all of that through using Mode Frontier. So in terms of Mode Frontier itself, it has a wide range of tools for us to be able to do that, to understand our design space, either to visualize it in terms of response surfaces, to plot some charts, to understand some of the relationships, and look at some of the multivariate analysis. So let's go straight, hopefully, into the demonstration and be able to look at some of those tools. So the first thing I would like to show you is just the data that we're going to import. We've just got quite a straightforward Excel spreadsheet. The data itself is not really that important in terms of what the columns mean, but we've got a series of input values, and then we've got some output values that we want to extract. Notice that some of the data is errant data, some of the are actually constants. So the data itself is not necessarily clean and tidy data, but we're going to get Mode Frontier to read that in a nice, efficient manner. So inside Mode Frontier, we can build ourselves a workflow automatically straight from that Excel spreadsheet, or we can go straight to the design space and use the table creation tool to load in that data. We can either get it to build a workflow and then a corresponding table, or we can just build the table on its own. Either way, it doesn't really matter. But in this case, we're going to use this data wizard. And we're going to tell it to open from a file. We'll find that initial data set, and it will open up this little wizard to be able to import that data from that Excel. Notice that it's already found the columns and the rows and trimmed off anything that's just blank data in terms of columns or rows. We click next. And then we can start tidying up the data. So if I wanted to extract the variables from the first row, or extract the ID numbers of the designs from the second row, I could remove columns that I'm not interested because they're just purely constant. Just bear with me. And then where there are numbers, not the numbers, we can start removing those rows as well, just to tidy those up so that we don't have to deal with those. Maybe they've been generated in error. Just get those tidied up. And once we're happy with that, we can click next. We can then associate certain rows and certain columns to inputs. So we can select those as inputs, and we can select these two columns as outputs. And once that's done, we can just click next through and click finish. And it's built a workflow that we're not going to use. But the important thing is that if we wanted to generate the results rather than importing it from an Excel file, but wanted to generate it through a CAE process, we could get it to generate it through some tool. But in this case, we've opened up the design table and all of our data has been inputted here. Now I notice that there is one design that's still red because I didn't clean it up entirely when I imported it, but I can select that and delete that. And if I really wanted the ID numbers to be exactly the same, I could right click and I could tidy that up and say reset ID so that they're all in order and there are no gaps in our data. Okay, so the first thing, and I think most of the tools that we're going to look at today are in this section down here. which is the statistical charts area. But we're going to borrow one from the design charts, which the first thing is the design distributions bar chart. This is a nice way of being able to understand first and foremost whether or not the distribution of our data is even across our design space. So what this is showing is that for each one of our variables, I can look on here and I can see that this cell represents all the values between 6 and 7.2, and if I go up, it goes up that variable range, and then it shows on the left how many designs are in that region. So we can see here that we've got 71 designs in this cell, but only one design in this cell. So it's saying that for delta P, the distribution is that there's a lot, it's unevenly distributed across this variable. But that's okay, because that's the outputs. But we're looking at the distribution among the inputs. Are all of the colors broadly the same? And we can see that our data is not evenly distributed. We've got many more designs looking at wrapping in the lower range than we do have in the upper range. So that's a first way of data mining and understanding the quality of our data. This is important because when we start doing some other statistical tests later on, we may need to have this quality of data. Now, then another way of looking at that data is to look at this correlation matrix. Last time we looked at some of the statistical tools, especially using this statistical tool at the top, which doesn't require such well-distributed data. But here we can look at some of the values that it's telling us in terms of the relationships. If I was just to do the inputs, actually, the relationships between just the inputs. And this is telling me a value between -1 and 1 of the correlation between these variables. So it's telling me that D2 is correlated to beta 2 with a value of 0.324. Now, typically when you're looking at inputs against inputs, it doesn't matter how much you change one input, it actually has no relationship on the other input. So all of these values should actually be 0, and the reason that they're not 0 is purely because of the quality of the data, or the way in which we've sampled our design of experiments. And we can so see this, that the data that we've got is not necessarily a very good quality. Now, if I wanted to get a much better quality of data, I could use Mode Frontier to generate a new table of data, and rather than using this set of data, I could generate a better distributed set of data. So like this set of uniform Latin hypercubes, 40 of those, and if I was to plot the same chart on that set of data, then I would see that my correlations would be much closer to 0. So if I was to use this set of data, then I could perhaps use it for some of the statistical measures that we're going to look at today. So I'm just going to pop that data back into that design table. But we're going to continue anyway with this poor set of data, and we're going to ignore, for the time being, some of the relationships. Just having a little look here. So we've looked at the relationships between the inputs on their own. Now we could add the outputs, and if we were to establish that the inputs had a low correlation, now we could start looking at the efficiency and the delta P, which are our two outputs, and start making some conclusions about their correlation. If I was to filter out anything that has less than 0.6 correlation, then we could start seeing that the strongest relationships are blade shape and beta 2 with relation to the efficiency. And then I could start moving down the filter and seeing which is the next strongest correlation. So that's doing it in this triangular form. It is also possible to do the same plot, but using a rectangular correlation chart, and this way I can select on my y-axis, I believe to be, or my inputs, and my y-axis to be the outputs, and then we get exactly the same representation, but in a rectangular form, and it's probably a little bit tidier, not having every combination of inputs to outputs. So they're nice ways of just being able to represent this data, and first of all looking at some of the correlations. We can also relate those values to their scatter plots, so we can use this scatter chart tool, the same way I plot my inputs and my outputs. We have the same data down here looking at our relationships, but we can also associate that relationship to the scatter. Where I click on one cell, it highlights the equivalent data. Now notice this is a negative correlation of 0.8, so that's very strong. It's quite close to 1. If I were to then plot a regression line through it, you would see that there is a negative regression line of the relationship of beta 2 to efficiency. So you can see why that result is like it is. So this is a positive 0.6, and again, we can do that. We can pop these out and look at them in more detail and look at the distributions. We could also have just a little look at the correlation of just our outputs against our outputs, and this could be an interesting one, is to see whether there's any relationship between our two outputs. If there's no relationship between our two outputs, then you might be able to say, if we were to try and optimize this, whether or not there is truly a multi-objective optimization. Because if we're trying to trade off these two objectives, that would be quite difficult if they don't actually have a genuine relationship between each other. Additional things, if we were wanting to look at outliers, we have box and whisker plot charts. So we can, I believe, let's just get the right chart for a second, this one here. And we'll plot this for our two outputs. We'll do that on separate charts actually. We'll do one on delta and one on efficiency. So this just gives us a representation of the data in terms of its mean, its quartiles, and we'll notice that the efficiency has a particular distribution, but the interesting thing for delta P is that we have also on here an outlier. So there's one design located up here, design 11, that is actually an outlier that is far away from all the other design points. Now you can notice when we go back onto the scatter chart that I've highlighted it on this chart here. That means it's also highlighted in all the other charts, and you can see that delta P against efficiency, it's this outlier here. Now if you're to remove this, it would probably change this chart. So I could go to my design table. It's also marked in my design table as ready for me to delete. So I could then remove that particular chart, and then that alters how the scatter graph is shown, and then we could look in. So we can clean up and tidy up data using the box and whisker plot charts. We can also look at the factor analysis. So not only look at the main effects, so when we've been looking at this correlation, we've really been looking at the linear correlations between the main effects. Now what happens if you want to start looking at some of the interaction effects? Well, we can use this factor analysis table. So we've got two windows, one each for each output. So here, looking at efficiency, there's a number of charts. It's all really telling us the same story, but just giving us different tools to be able to look at it from a slightly different angle. So here it splits each data set into two, giving it sort of box and whisker plots for each, and then we've got a line between the mean of each of the box and whisker plots. Now if there's a large variance between the upper and lower part of the data, then we can start saying that there's a correlation for that variable. So in this case we could click on beta 2 and think, well, that's probably got the highest correlation. If I was to look at the absolute effect in this chart and order it, then beta 2 does become at top of the list as being the highest contributor to efficiency. We also see it in this plot as well, where we look at the absolute effects against the half normal quantiles. You just have to imagine a normative line going through this point, and typically where you get designs that are off the end and off the center line of these points, these will be the factors that we'll be most interested. So in this case, we're looking at beta 2, and then here, when I click on this one, this is actually an interaction of the blades and D2. So we can see that not only which ones are the highest main effect, but also whether or not the interaction effects are also interesting as well. In addition, we can look at some of the student plots. So again, looking at our outputs against our inputs. So again, ranking the main effects of each of the inputs to our output. But this will give a little bit more information, because it gives you a numeric description of the effects. So we can see which one has the highest effect. Again, we know that beta 2 is the one that has the largest effect. But we can also look at the significance, so whether or not we can trust this effect. Okay, this is telling us that beta 2 has the greatest effect, but can we trust it? Well, the significance has to be as low as possible. So this is saying that, okay, we can actually therefore trust this particular effect size. Now, if you're familiar with t-tests, t-student test, then all those equivalent values are presented here as well. Those same results can also be plotted in a different format. So if we wanted to look at the student charts, but also in terms of a pie chart, so the biggest effect is beta 2, which is this one, and we can see which ones make up the pie chart. So that's just showing the similar results, but in a different format. Now, if we wanted to see that in 3 dimensions, we could also go on to this final chart, which has all of the inputs against the outputs against their effects as well. So that's a way of plotting all of those in a 3-dimensional format. So I believe that's everything that I really wanted to cover with you today. I know that there's probably a lot more that could be gone into, especially in terms of the mathematics and the details between how you would actually understand some of these values. But I hope that's been helpful and given you some kind of food for thought. It's now open to any kind of questions that people wish to ask. Please type them away if that's okay.